Hi everyone, in this video I'm taking a look at this interesting trigonometry question which comes from the NRICH website. Now if you haven't heard of NRICH before, it's a really great resource for both teachers and students that let you dive a bit deeper into various high school math topics. So I discovered it through my Master of Teaching program and I've just found it to be a really excellent resource. So I'll give a link to it in this video so you can find it easily. For this particular question, we're given this diagram and we're told that we've got three right triangles all sharing the vertex A, and then we're asked to find the length x. And in the diagram, we're told where certain angles are. We're given the length of one of the sides being 1 centimeter, and then we've got our value x that we're trying to find. So what I'll do is I'll put a little break in the video so that you can press pause and have a go yourself. And then we'll come back and I'll show the way I think about this question. Alright, so here I've recreated the diagram as best I could. It's probably not perfect, but it's good enough for what we need to do. So we've got our three right angled triangles, our common vertex A, a few of the angles that we're told, this length here of 1 centimeter, and then the length we're trying to find, which is x. Now I think, I'm not sure whether you did this if you had a go, but for me, I think what's really helpful is to redraw this diagram and separate them into the three triangles, all kind of in the same orientation. Because I think having the 90 degrees in different places for the different triangles and having them all rotated makes it a bit harder to visualize what we're dealing with. So I think step one to being able to draw these triangles is, I think, to label all the points so we can easily refer to them. So what I might do is, in a new color, I'll just give each of these points a name, and that's just going to make it that little bit easier to reference all the triangles. So we've got A here, so let's call this B, C, D, and E. And now what I'll do is I'll just draw up these triangles, and I'm going to quite deliberately put them all so that their right angle is all in the same place. And these triangles won't necessarily be to scale in terms of the actual original diagram, but I don't think that's necessarily important. I think the most important thing is making sure that I put the right information in the right spot on each triangle. So notice here what I've done is I've put all the 90-degree angles in the same spot. So now we've got to work out where the various points are. So we know that they all share this common vertex and point A, and point A is always at the top of each triangle. So that's easy enough. We can say this top point for all three triangles is point A. I think next we can look at which point is at the right angle for each triangle. So in triangle ABC, point C is at the right angle. And that means point B must be the remaining point for this first triangle. So that's ABC. For the next triangle ACD, again point C is at the right angle, which means this must be point D. And then in the last triangle ADE, it's point D that's at the right angle. And then it's point E, which is the other point. In terms of the angles we're given, so we're told that angle BAC is 30, so BAC is 30. We're told that CDA is 60, so CDA, that's 60 there. And then we're told DAE is 30, DAE, so that's 30. We're told that the length of BC is 1 centimeter. And then the unknown we're trying to find is AE, which is x, so AE, so that's this one here, the hypotenuse. So that's all the information we're told. Now let's overlay onto that some information we can work out using trigonometry. And I think the first set of unknowns, I think, can be the remaining angle in each of these triangles, because we know that all the interior angles of a triangle add up to 180 degrees, and given we've got right angled triangles and one of the remaining angles, it's fairly easy to work out the remaining ones. So 90 plus 30 is 120. To get to 180, we need another 60 degrees. So this angle must be 60. Similarly here, if we've got 90 plus 60 is 150, then this must be 30. And here we've got 90 and 30 again, so this must be 60. And notice all of these angles in these triangles are the same. So right away we can think, are they similar triangles? Are they congruent triangles? Let's have a look. Well, I think with these first two triangles, because they've got all the same angles, and we know one of the sides is the same, AC, AC, well, we can actually say these triangles are going to be congruent, which is going to really help us. So I've used the angle, side method there to say these triangles must be congruent, which means actually if this length BC is 1, then this must also be 1. And actually this triangle is not just any old triangle here, both of these. It's actually quite a well-known triangle where as you learn trigonometry, you'll learn there's some fairly important angles, 30, 60 and 45 being another, but here the most relevant ones are 30, 60, and it's actually whether you memorize it or not, it depends. Often on important exams like say the HSC, you'll be told that in this particular right angled triangle where we've got the 30, 60, 90, the sides are actually 1, 2, square root of 3. And for me, I've seen that so often that it's kind of etched into my memory. But it's not uncommon, depending on the context, that you might actually be given this in say, a cheat sheet or something. But I've actually made a video about this triangle and the other important triangles. So I might give a link to that video if you want to go take a look. It's just talking about these triangles and how maybe a helpful way to remember the various angles and the side lengths. But if this is 1, 2, root 3, then I know because these two are congruent, this must also be 1, 2, root 3. So I think that's really going to help us in eventually working out the length of x. Now, where we had AC being the same in these two triangles, we've also got another same side in these two because we've got AD and AD. And when you originally look at the original diagram, it might be hard to spot that, but here AD is the hypotenuse of this triangle, but it's actually just one of the other sides of this one. But I can use the fact that they must have the same length because they're the same side, so this must be 2. And I think kind of now that we've annotated on all that extra information, we're in a really good position to find x. And we can do that using the kind of classic SOHCAHTOA rules, which hopefully you've learned. And in particular, I mean, I can pick either of these angles, but if I pick this angle here, what I can say is that in triangle ADE, I can say that the sine of 60 degrees will be equal to the opposite over the hypotenuse. So 2 divided by x. Now I want to rearrange for x, so I'm just going to bring the x up here and the sine 60 down. So we have x is equal to 2 on sine 60. And at this point, you may just go, I'm going to throw that into my calculator and evaluate it. But actually, because we're dealing with this well-known angle, we can actually find the exact value before necessarily putting it into our calculator. Because I know sine 60 is root 3 on 2, opposite over hypotenuse. And so I can say that's going to be equal to 2 divided by root 3 on 2. And then if I just kind of clean this up a little bit, it's basically going to be the 2 will come to the top, so 2 times 2 is 4, divided by the square root of 3. And then at this point, we could leave it there if we wanted, but we could then also get out our calculator and do 4 divided by the square root of 3, and that's going to be 2.31, say I'll just round that to 2.31 centimetres, because the units we're dealing with are centimetres. So that's it for that question. So as you can see, it's a really nicely written question. It goes a little bit beyond just saying, use the SOHCAHTOA rules or use the rules of congruent triangles. You're not necessarily given that nudge, but if you do know that content, you can then work this out. And I quite like it because we're given this odd shape. If you kind of just look at the outline of the original shape, it's not a kind of common shape. But what it's kind of hinting at us is that most, if not all, shapes can be broken up into a series of triangles. And if we use our knowledge of triangles from trigonometry, we can then find things out about shapes. Even if the original shape isn't a triangle, we can break it up into triangles. And in particular, right-angled triangles, that lets us really make use of particularly SOHCAHTOA. And then Pythagoras too, which we didn't need in this question, but that's a common piece of knowledge that we can take advantage of. So hopefully you found that interesting and you were able to follow along. I think the key to this, at least for me and the way I think, was to get these 3 triangles all in the same orientation, because then the congruency really jumped out and things followed along from there. So hopefully you were able to also get to this result, and that was an informative exercise for you. And tick boom.